Okay, let's dive right into this explainer. Today, we're decoding the invisible chemical laws and mathematical formulas that literally dictate everything, from the fizz in the soda you drink to, well, actual human survival. You might not realize it, but almost all processes in your body and in the world around us occur in some kind of liquid solution. We're going to unpack the hard science, the specific calculations, and the high-stakes physical realities of how substances mix, dissolve, and react under pressure. We're going to build this step by step. So we've got the anatomy of solutions, concentration formulas, crunching those numbers with mole fractions, the rules of solubility, Henry's law in action, and finally, high-stakes chemical survival. Let's get into it.
Section 1, the anatomy of solutions, the fundamental building blocks.
To really grasp these physical processes, we've got to master the basic vocabulary first, right? Because we cannot calculate what we can't define. At its core, a solution is just a homogeneous mixture. And by homogeneous, I mean its composition and properties are completely uniform throughout. Inside this mixture, you've got a clear hierarchy. The solvent, that's the component present in the largest quantity. Think of the solvent as the boss. It completely dictates the physical state of the solution, whether that's solid, liquid, or gas. The other guys in there, the ones in smaller amounts getting dissolved, those are your solutes.
Moving right along to Section 2, concentration formulas and measurements.
Now, we need to figure out exactly how much of a solute is hiding in our solvent. In chemistry, just knowing the ingredients isn't enough. You need the exact numbers. Take parts per million, or ppm. It sounds kind of abstract, right? But it has a profound physical impact. We use ppm for unbelievably tiny concentrations, like trace minerals in your water. For example, just one single part per million of fluoride ions in water is the exact perfect sweet spot to prevent tooth decay. It is a tiny, microscopic amount doing a massive biological job. But check this out. If you bump that concentration up just a tiny bit to 1.5 ppm, the whole chemical reality shifts dramatically. Your teeth actually become mottled. And if you keep increasing that concentration, there's no way around it. The fluoride literally becomes rat poison. That is how incredibly fine the line is between a medical benefit and a lethal dose. Precision is absolutely crucial. So, to track these high-stakes concentrations, chemists rely on specific mathematical languages. The two big ones are mole fraction and molarity. Molarity, represented by a capital M, is super common in the lab. It's just the number of moles of a solute dissolved in exactly 1 liter of solution. Simple enough. But mole fraction, which uses a lowercase x, is a real game changer when we're calculating gas mixtures or relating concentration to physical properties like vapor pressure. It's simply the ratio of the number of moles of one specific component to the total number of moles of everything in the mixture.
All right, Section 3, crunching the numbers with mole fractions. Let's actually put this formula to the test in a real-world scenario. Say we're presented with a binary mixture, meaning a mixture of exactly two things. In this case, it's ethylene glycol dissolved in water. So, how do we find the exact mole fraction of our solute, the ethylene glycol?
Well, we just break the math down logically into 3 steps. Step 1, isolate your solute's moles. Let's say we're given 0.322 moles of ethylene glycol. Step 2, find the moles of your solvent, water. We'll say we have 4.444 moles. Step 3 is where the formula comes to life. You just divide the moles of your target component by the total sum of all the moles in the solution. So you add 0.322 and 4.444 to get your total.
And there you go. It cleanly gives us a mole fraction of 0.068 for the ethylene glycol. It's just 0.322 divided by the total of 4.766. It really shows the elegance of the formula. Oh, and here's a beautifully perfect rule. The sum of all mole fractions in a given solution is always exactly 1. So if we wanted the mole fraction of the water, we just subtract 0.068 from 1, giving us 0.932. It's a completely closed mathematical system.
Which brings us to Section 4, the rules of solubility.
Okay, we've got the math down, but what actually decides if these solutes will dissolve in the first place? Well, solubility isn't some frozen, static state. It's a constant, dynamic tug-of-war. When you add a solid solute to a solvent, it dissolves, increasing the concentration. That's dissolution. But simultaneously, some dissolved particles are bumping into solid ones and separating out. That's crystallization. Eventually, you reach a state where both processes are happening at the exact same rate. The amount going in equals the amount coming out. We call this dynamic equilibrium, and it gives us a saturated solution. It's basically holding the absolute maximum amount of solute possible for that specific temperature and pressure.
So what happens if we mess with the temperature? Following Le Chatelier's principle, temperature acts as the ultimate controller here. If a dissolution process is endothermic, meaning it actively absorbs heat, cranking up the temperature will actually increase the solubility. The heat helps it along. But if the process is exothermic, meaning it releases heat, adding more heat will actually hinder the process, decreasing solubility and forcing the solute right out of the solution.
Let's move over to Section 5, Henry's Law in action. When we start talking about gases dissolving in liquids, pressure takes over as the main driving force instead of temperature. Way back in 1803, William Henry gave us a strict mathematical formula for this. P equals kH times X. To put that in plain English, the partial pressure of a gas above a liquid, that's the P, is directly proportional to the mole fraction of that gas dissolved inside the liquid, that's the X. kH is just your constant. Mathematically, it proves that if you apply higher pressure, you literally force more gas molecules into the liquid solution. And this one invisible chemical law governs a massive amount of the world around us. It's the exact reason soda bottles are sealed under such high pressure. You have to physically force that carbon dioxide into the liquid. It also explains why aquatic life actually thrives in cold water. Counterintuitively, the solubility of gases like oxygen increases as temperature decreases in liquids. But most importantly, it dictates some serious medical phenomena when humans push the limits of their environments, like scuba divers or mountain climbers. Which perfectly tees up our final part, Section 6, High-Stakes Chemical Survival. Let's look at what happens when human beings push the limits of Henry's Law to the absolute extreme, where getting the math wrong is quite literally fatal. When scuba divers go deep underwater, the immense physical pressure increases the solubility of atmospheric gases in their blood. If they just breathe normal air, dangerously high concentrations of nitrogen would dissolve into their bloodstream. If they come up to the surface and the pressure drops too fast, that dissolved nitrogen suddenly releases, forming bubbles in the blood capillaries. It's a painful, highly dangerous condition called the bends. So to survive, they absolutely cannot breathe normal air. They rely on a mathematically precise diluted mixture in their tanks, exactly 11.7% helium, 56.2% nitrogen, and 32.1% oxygen. The helium dilutes the whole mix, keeping those toxic nitrogen concentrations safely in check. On the flip side, look at high-altitude mountain climbers. Up there, the partial pressure of atmospheric oxygen is way, way lower than at sea level. Following Henry's Law again, this low pressure means far less oxygen can actually dissolve into their blood and tissues. This dangerous drop induces anoxia. Climbers become weak, confused, and unable to think clearly. Once again, it's just human biology at the total mercy of a liquid solution trying to find its equilibrium. It really makes you stop and think, doesn't it? Our everyday reality isn't just happening by chance. From the exact mole fraction of oxygen in the blood that's powering your brain right now, to the pressurized fizz in your favorite soda on your desk, every single breath we take and every liquid we interact with is entirely governed by these magnificent, calculating chemical laws. So the next time you crack open a sparkling drink, take a second to appreciate the dynamic equilibrium happening right before your eyes. It kind of leaves you wondering, what other invisible absolute mathematical laws are silently governing your reality at this very moment? Thanks for tuning into this explainer, and keep questioning the science around you.